So in the last video, we saw the definition of backward induction, and I gave you a slightly better way to check whether a given pure strategy profile is a subgame perfect equilibrium. So it turns out that there's actually a good method for computing subgame perfect equilibria kind of from scratch without having to start with a strategy profile and then check it. So this is called backward induction, and it's an extremely important method in game theory. So here's the backward induction algorithm. What we're going to do is, given a game tree, we're going to pick some node, any node, whose children are all leaves. And then we're going to pick any action at that node that maximizes the payoff for the player that owns that node. And we can do that because all of the children are leaves. We don't have to do any look ahead. And then what we're going to do is we're going to delete the node and we're going to replace it by the leaf that we get by following the action that we chose. So remember, the leaf is labeled with a payoff vector for all players. So this gives us a tree which is one node smaller. And then what we're going to do is we're just going to repeat. We're going to go back to 1 and we're going to repeat until all we've got left is a single leaf. And then at the end of doing this, what we've done is we've chosen an action at every node. So we're going to record the actions that we chose at every node when we deleted it, and all of that data together is a strategy profile. It's a choice of action at every node, and so that strategy profile is what we output. So here's an example. So here's the ultimatum game. In its initial state, we have two different nodes whose children are all leaves, namely this one and this one. So let's arbitrarily say that we choose this one first. So this is owned by player 2. So we need to choose an action which maximizes the payoff for player 2. Well, A leads to 5 and R leads to 0. So we better choose A. So what we're going to do is we're going to delete this node and we're going to replace it with the leaf 5-5 that we got from following A. So after doing that, we're left with this tree. Now this has only one node whose children are all leaves, namely this one. So now we do the same thing. We choose a maximizing choice for player 2. So A would lead to 2 and R would lead to 0. So we choose A. And so we're going to replace this node with this leaf. So that takes us to here. And now, again, we have one node whose children are all leaves, namely the root node. Now this is owned by player 1. And so choosing F leads to a payoff of 5, choosing U leads to a payoff of 8. And so player 1 is going to choose U, and then we're going to replace this node with just this leaf, which is A2, and then we stop. And at the end of this, we've chosen a strategy profile, namely player 1 chooses U and player 2 chooses A in both subgames, which, if you will remember, this was the unique subgame perfect equilibrium. So this is not a coincidence. So here's important fact 1 is that the strategy profile that you will get as an output of doing this procedure is always a subgame perfect equilibrium. And important fact 2 is that, so we had to make some choices at some point. We can choose the order that we delete nodes, and sometimes we get multiple maximizing actions and we have to arbitrarily choose one of them. But every subgame perfect equilibrium can be outputted by the algorithm given some choices that we could make. Okay, note, we've used finiteness of this game in 2 different ways. First of all, we're using the fact that every node only has finitely many children, which means it has some maximizing action. And then secondly, we're using the fact that the tree only has finitely many nodes. It has a finite depth, which means that this algorithm actually terminates. So it turns out that when we have a choice of multiple different nodes that we could delete, the order we do it turns out it isn't important. It's the genuine choices that we have are between when we break ties between actions that lead to the same payoff for the player who owns that node. Okay, So as a result of termination of this algorithm and the fact that its output is always a subgame perfect equilibrium, we had a consequence of this, which is that every extensive form game, as long as it's finite, has at least one subgame perfect equilibrium. So this is a very important result. Okay, here's a very interesting new example. So the centipede game is designed to be sort of paradoxical. Subgame perfect equilibrium leads to predictions which are extremely different to how humans play. So we have two players here who take it in turns to choose to quit or to continue. And if any player chooses quit, then the game ends immediately. And if they continue, then the game keeps going along this kind of spine. So we get this kind of lopsided tree. And I've drawn this for 4 stages, or 2 stages with 1 choice for each player. But the same idea can be repeated to any number of times. So that's why this is called the centipede game, because you can extend this to 100 legs if you want to. And if you look carefully at the payoffs, you'll see they're set up in this weird kind of alternating way. And this is what leads to its paradoxical behavior. So you can see that the highest payoffs here are reached along the bottom. So clearly it's going to be Pareto optimal for the players to reach somewhere down here. So let's see what happens if we do backward induction here to work out a subgame perfect equilibrium. So at each stage, we're going to find that we get always one node that we can eliminate, which is this bottom one. And it's carefully set up so that always quitting is the appropriate action. So here we're owned by player 2. If player 2 quits, they get 4. If they continue, they get 3. Of course, continue here sort of really means quit, because this happens to be the last stage of the game. So player 2 is going to choose the quit move. And so we're going to replace this node with the leaf 2-4. So now we get to this slightly shorter version. And now player 1 owns this. And if player 1 quits, they get a payoff of 3. Whereas if they continue, they get a payoff of 2. So now, if you think back to where we are in the original tree, you can sort of see what's starting to happen. Player 1 will prefer to go here and get an immediate payoff of 3, whereas if they continue, they could potentially get an equally high payoff, but actually player 2 is going to quit and then leave them with a lower payoff. Okay, so player 1 is going to quit, so we're going to replace this node with the leaf 3-1, and then the same kind of thing happens. And so again, player 2 is going to prefer to quit because they get 2 rather than 1, so going to replace this node with the leaf 0-2, and then we end up just here, and then it turns out that player 1 would like to quit immediately. And so the strategy profile that we've ended up constructing is that both players always quit no matter what, no matter where they are in the game, all players quit immediately. And this remains true even if this game was 1,000 stages long. So this is a kind of paradox, because when you get humans to play this game, they end up kind of not doing this, and they end up going some way. Humans typically end up going some way along the path of play before they lose their nerve.